Hey, this is the video for 1.4, the carbon cycle. So go ahead and check out the overview and set up your guided notes. So carbon cycle is the first of the biogeochemical cycles we will be discussing. Bio means living organisms, geo means earth or rocks, and chemicals means you just have different molecules. So biogeochemical cycles are molecules switching between different forms throughout living and non-living or biotic and abiotic factors. So the complete carbon cycle looks like this. This is what I have constructed. I'm going to say don't stress yourselves out on copying a lot of these formulas. I will give you the definition for each process that is involved in this entire carbon cycle. And there's a few steps that you really should understand. So for starters, the first process is photosynthesis. If I write a equation up here, commit it to memory, please. Now, photosynthesis is when you're taking atmospheric carbon dioxide and you're converting it into glucose. And this is signified by the red arrow right here. It is going into the plant. The next process is cellular respiration. Respiration, the formula, the equation is right here. It is the synthesis of ATP from the energy that's found in the bonds of glucose molecules. It gives off carbon dioxide as a result. Again, with the carbon cycle, we only are really concerned about the different forms of carbon. So we're starting with glucose, we're ending with CO2. Both animals and plants perform cellular respiration. The next process is decomposition. That's when we will have an organic form of carbon, and it is typically broken down into methane, carbon dioxide, and water. I chose methane. You should understand the formula for methane is CH4. Methane we will be discussing throughout this entire year. It's very troubling because it has a warming potential that is 25 times more severe than carbon dioxide. But methane is also another natural gas is composed of predominantly methane. So whenever we have decomposition, we're breaking down this organic matter. And for something to be organic, it has to have carbon and hydrogen. So this is a very simplified formula, CH2ON. The N is just any variable. You can add hundreds, even thousands of subunits there. The next one is gas exchange. And gas exchange is when you're moving carbon dioxide between different components within the cycle. This is done through metabolic processes. It's also done by dissolving in water. So carbon dioxide can dissolve in water to form carbonic acid, but also carbon dioxide can move back and forth, gas exchange between the plants. Carbon dioxide goes in, you might have oxygen coming out, and also carbon dioxide is coming out from cellular respiration. Assimilation. Assimilation is when you're taking a form of carbon and converting it into organic carbon molecules. In other words, you're making it part of your own body. So you're assimilating these aquatic organisms are assimilating the carbon dioxide or the carbon into their shells. Animals are assimilating the glucose into their body tissues by eating other organisms. Plants are assimilating CO2 and forming it into glucose. So all of this is an example of assimilation. Sedimentation is when you have the accumulation of organic carbon or inorganic carbon as well, like calcium carbonate, and it accumulates at the bottom of the ocean. So you have all of this material that is from the shells and the body tissues of organisms that ends up accumulating on the bottom of the ocean. Fossilization is when you convert this organic carbon molecules into minerals. So when you're forming coal, oil, and natural gas, that is fossilization. Also when you're replacing the organic material with mineral material, as is the case with fossils. Then we have uplift. Uplift is when you have tectonic activity, and we'll talk about tectonic activity in the future, but when you have this rock, like in the form of limestone, moves up towards the surface of the earth because of the actions beneath the earth's surface. And then we have something that is not really normal. Humans have only done this for the last 150, 200 years. It's extraction. And that is when we're removing this ancient carbon fossil fuel and we're using it for human use. So it's been locked away for millions of years, and then we discovered that it has a lot of energy, so we've been digging it up and using it. And the reason it's all bad is because of this term combustion. Combustion is when you burn a carbon-rich compound in the presence of oxygen and you're forming carbon dioxide. Now, combustion can happen with the forest fire. Combustion can happen through volcanic activity, although it's very low, the amount. But most of the combustion happens from the burning of fossil fuels, and that is what's contributing to the high levels of carbon dioxide in the atmosphere. How do we know this? Well, I'll talk about it. We've been locking away carbon for a long time. And when we lock carbon away for a long time, it's called a carbon sink. Like, think about the sink in your bathroom in your kitchen. You put water in there, you put something in there, it goes away. Now, a reservoir is something that is used temporarily. So temporary reservoirs are ones that are readily available, and a carbon sink is when it's locked away for a long period of time. So the reservoirs, typically ocean, carbonic acid is a reservoir, carbon dioxide in the atmosphere is a reservoir, and some of the carbon dioxide or the carbon that's stored in more recent organisms like living animals and some of the younger trees will be a carbon reservoir because it's readily available. Carbon sink is when you lock it away for a really long time, like this sedimentation, the rock sediment at the bottom of the ocean, and fossil fuels. Now, we've noticed that the carbon dioxide has increased over the past 50 years, and we know this because we've taken samples of carbon dioxide. If you notice here, we have up, down, up, down, up, down, up, down, up, down. It goes up and down. The carbon dioxide levels will actually increase in the winter, and they will decrease in the summer. Now, that is in the northern hemisphere because most of the photosynthesis that's happening in terrestrial biomes is happening in the northern hemisphere because of all of the boreal forests and the taiga. So this has been happening, and it's been steadily increasing over the last 50 plus years. And we've taken these samples from Mauna Loa in Hawaii. And the reason for that is because Hawaii is very isolated. It's not getting a lot of carbon dioxide from other areas, so you're getting a very pristine sample. So they've noticed that the levels have gone up. Now we're well over 400 parts per million. I remember when I started teaching, 400 parts per million was like that really dangerous level to be at, and now we've exceeded that. So question, what is the percent change of carbon dioxide between 1990 and 2000? So what you have to do is we got to look up 1990, we got to look at 2000. In 1990, it was 355 parts per million. In 2000, it was 370 parts per million. So when you're doing a percent change, the formula is, and write this down, commit this to memory, you have to know how to do this. So percent change is final minus initial over initial times 100. So let's substitute. We have 370 minus 355 divided by 355. In other words, 15 divided by 355 times 100. That gives us 4.2%. I would like you to respond to this check for understanding. And now it's time for the FRQ practice. I want you to explain how a carbon sink can reduce atmospheric carbon dioxide levels. I hope that this video was informative. I thank you for your attention, and I will see you soon.